Okay, so welcome everybody to this new DaSCI seminar. Today's speaker is Valentyn Melnychuk, and I'm very sorry if my pronunciation is not correct.
Perfect.
He's a fourth year PhD student at LMU Munich, supervised by Professor Stefan Feuergigel and co-director of the Causal ML lab at the Institute of AI in Management. Previously, he was a research assistant at the Fraunhofer Institute for Integrated Circuits in Munich, and his research focuses on causal machine learning, causal inference, and probabilistic modeling, topics on which he has co-authored scientific publications in top conferences and journals, such as ICML, AAAI, NeurIPS, iClear, and Nature Medicine. Today's talk will be focused on causal ML for predicting treatment outcomes. I want to thank again Valentyn Melnychuk for very kindly accepting our invitation, and whenever you're ready, the floor is all yours.
Okay, thanks a lot, Pablo. Want to say hello, everyone. Yeah, I'm very happy to be here, happy to present at the seminar. And yeah, just gonna talk about basically roughly 4 years of work, of my work, also work in our lab. We are almost like this Causal ML lab. We have roughly 8 PhD students. Now we also have visiting PhD students. So we are expanding. Today I want to talk about the usage of causal machine learning, especially in the medicine. And I would start with the great vision that what kind of promises that causal ML machine learning has for treatment effect estimation, for example. So in a nutshell, it's a very powerful tool to basically augment evidence from randomized controlled trials. And in many scenarios, we can even do something that randomized controlled trials cannot do or unethical. And the causal machine learning can allow us to scale and basically individualize treatment to every single individual. So here you might see the basic overview. Today I will make a lot of references to our Nature Medicine paper from 2020, from last year. That's more like a perspective where we say what could, like, where we basically describe our vision and provide some background information of what a machine learning researcher who wants to apply to the medicine, what should they start with? And causal machine learning is that's basically one of the main points of my presentation today. It's very different from the traditional machine learning, because traditional machine learning would only provide us with some diagnostical data, or to allow us to do, for example, risk scoring. So we say we kind of observe some progression of like probability of patient survival, and we know the person is not treated, and then we can sort of, the traditional machine learning could do the predictions of what would the future survival curve look like, given also that the same kind of environment stays, so we don't have any treatments. But the causal machine learning asks a different question. We ask simultaneously several questions. For example, we say, what would happen to this person if we actually treated them? So we kind of ask this kind of different, I can call it counterfactual questions, given, say, or what also the traditional machine learning is kind of encapsulated inside of the causal machine learning. So we can also predict a regular curve under the traditional treatment plan, and we would be able to predict some kind of counterfactual treatment plans. And if we can, then we can also compare those treatment plans, take a difference, and this we would call a treatment effect. So roughly speaking, we have a fundamentally different problem that we try to solve. I'm gonna have several other intuitions how it is different in a moment, but the holy grail here is that we want to get some kind of real world evidence from the real world data, or we also call it observational data in the causal or machine learning community. And usually the real world evidence is being obtained through the randomized control trials, but they are very costly or often unethical. So we ask the question, what would be the steps to use the real world data or observational data? As it turns out, it's very challenging. For example, we might collect observational data on, it's like a very toy example. We have a sunscreen usage as a binary treatment, and then we want to know whether it has an effect on your probability to drown in the ocean or in the sea. So we also collect the number of drowning-related deaths. And yeah, as I said, we aim to estimate the effect of the sunscreen on the chance of drowning. If we just use, like, just collect the raw data and do some basic statistical inference, we might think that the higher the usage of sunscreen, the more likely for a person to be also drowning. But it kind of goes against our own intuition. Of course, there is no causal connection here. So apparently there is something that we didn't account for. And this something is basically the phenomenon of hidden confounding. So there is actually a third variable, or a third kind of covariate, which we also need to measure, which kind of influences both the sunscreen usage and your kind of probability to go swimming, and that's why also your probability to drown. And now we say if we collect this additional data on the sunscreen or on the sunlight intensity, and then we do for every fixed sunlight intensity, we check how many people use sunscreen, how many people drowned, we would see there is no actually association there. So in this case, we say the real world data has a hidden confounder. And just to repeat again, there is a lot of value still in the real world data, even though it has those risks of hidden confounding. For example, if you don't have a standard care at all, or there hasn't been done any randomized controlled trials yet. Also, if you wanna know what's the optimal dosaging, if we have multiple combinations of treatments, again, as I said, when the RCTs are unethical. And the last one is basically when we want to provide a better personalization. So for example, here you see the average treatment effect might be like kind of high, but then there are still some subgroups of population, for example, young people for whom it's almost not effective, and for older people, it's like very effective. So the sort of personalization would allow to kind of have to apply the lowest amount of treatment, and then to know that, okay, if we applied that it's actually super effective. So we can make better treatment policies. Also, yeah, I didn't say if somebody has a question, or I guess because you record me, I guess I should just go through the whole presentation and then people might ask questions, or is it okay with interruptions?
Yeah, well, as you want, Valentyn. In fact,
yeah,
tell me, please.
Yeah, you can interrupt me anytime then. Just
okay, perfect.
Raise the hand or write the message.
Okay, perfect.
Yeah. Just want to provide a short introduction on what causal machine learning is. So, as you might, I've seen, you already had other causal presentations in this seminar. So, just to kind of destroy the ambiguity of the definition. Causal machine learning in the broad community, it could be both. So it could mean that we use causal inference for machine learning, for example, we use the concepts to better define or better describe the problems that we encounter in the machine learning or deep learning. So, for example, explainability, fairness, algorithmic recurse, robustness, or domain adaptation. So we just make existing machine learning models kind of better by making them kind of causality aware. But there is also another topic which we also call causal machine learning, where we have inherently causal inference problems, for example, predicting treatment outcomes like we do, or counterfactual inference or causal discovery. And then we use the machine learning and deep learning simply as like a toolbox. And then we say, yeah, once we kind of established some results here, we kind of use whatever model that is at hand, which would kind of satisfy our needs. And in my presentation, I say causal machine learning. I really mean the prediction of treatment outcomes. Also, small recap. Maybe you have heard the way to basically categorize all the causality. There's this Pearl's layer of causation, so which basically sorts out all the possible kind of statistical knowledge that we can get from data into like 3 layers, and those layers correspond to the like 3 categories of questions that we can ask about the world. And so the first layer is associational, when we ask like what's the probability that one event kind of happens together with the second event. Yeah, or for example, what does a symptom tell me about the disease, etc. The second layer is the interventional level, or more like experimental, where we ask, saying like, what if I actively change this variable? What would happen to some outcome, or what would happen to variable y? So here we say, for example, if I take aspirin, will my headache be cured in the future? And there is also counterfactual level, which is even more complicated, where kind of refers to retrospective questions, but retrospective questions when we try to make an intervention in the past. So here we ask basically questions of why something happened. Was it that one thing caused the other? And it's kind of like this kind of the interventional questions in the past, saying like, what was it the aspirin that I took that stopped my headache, or would it stop even without aspirin? And yeah, the traditional machine learning basically only works on this associational level. So we have both the data and the questions that we ask are both in the same level. And causal machine learning moves beyond that. And now we say, we try to answer the questions of, yeah, what would happen if I actively prescribe you the drug, or what would happen if, what would happen if I apply some treatment plan to this patient in the future? And unfortunately, as you see below, there we have the causal hierarchy theorem saying that we can only do the statistical inference from the data of the same layer or higher. So if you want to do kind of causal machine learning and we only have observational data, we need to make additional assumptions. And that's a little bit unfortunate for AutoML people, or when we want to have this automatic machine learning or some machine learning model telling us to, how to, like, what sort of drug is effective or not, just from observational data. And yeah, I will further talk about those assumptions in a very briefly. And let's talk about the specifically our task of predicting treatment outcomes, which is either treatment effects or potential outcomes. So in a very broad, the very broad description of the problem is that we have the IAD observational data set. We have X covariates, A is denotes treatments, and Y is the outcomes. They are here. We assume they are continuous, and essentially, imagine we have this data set where for every patient we see that we collect those covariates. We see that they were either treated or not, and then we kind of observe the corresponding outcome. We say, okay, if they were not treated, then we observe their outcome, like potential outcome of not treating, of being not treated. And for those who are treated, we observe also the corresponding outcomes. But what we want to identify or estimate at the end are either treatment effects or potential outcomes. So essentially, we want to kind of predict those missing observations. So in a broad sense, the treatment effect estimation is kind of missing data problem. So we, for example, if we say for a new cohort of patients, we want to predict both Y0 and Y1, and the treatment effect is their difference. So yeah, you might immediately see that, for example, the treatment effect, for every single patient, we never even observe it. We only observe one of the outcomes, not the other one. So strictly speaking, if you would want to use the classical machine learning like regression or like linear regression, or you'd want to fit the neural network, you just don't have a kind of target variable to fit it with. And then kind of this whole causal machine learning tries to find a workaround for this kind of missing data problem. And here is a very general workflow if you would want to apply the causal machine learning algorithms in real world. I will start with the problem setup. In this section, we don't use the data yet. We rather talk about the metadata, saying like what kind of covariates we have, what are the what is the treatment, what is the outcome, and what do we even want to learn, or is it possible to learn? So again, we need to define the quantity of interest. We might be interested in average treatment effects, for example, average treatment effect or average potential outcome. We might be interested in also more individualized effects. Say like for me specifically, with my characteristic, what would be the treatment effect or also potential outcomes? And also, as you remember, we had this causal hierarchy theorem saying like we need some assumptions, and there are basically two kind of school of thoughts here. We have the potential outcomes framework and structural causal models, which kind of encapsulate the assumptions on the causal graph. And the assumptions here rather stem from some structural knowledge. So we know that, okay, the patient covariates, they are kind of pre-treatment, so they influence the treatment assignment and the outcome. There might be some latent variables between covariates and the outcome, but at the same time, there shouldn't be any with X and A. So there's the whole theory how to know whether we can get the treatment, the causal effect from the causal diagram or causal graph. There is also another kind of narrow school of thought where we make a very kind of general statement in the language of potential outcomes. This one is stems from econometrics, but those assumptions are somewhat very like abstract, and you cannot really test. Like some of them you can test with the data, but for example, the third one kind of assumes there is no hidden confounders except for those that we already recorded, and it's impossible to check given or to verify given observational data. But at the end, in terms of the learning algorithms that we use, the both assumption frameworks, they give the same kind of recipes how to design those algorithms. So there is kind of this duality between them. And here is an example of a case study to do this kind of problem setup. So we want to estimate the heterogeneous treatment effect of development aid on the goals of the sustainable development. And here we can define the treatment as the amount of development aid. The outcome would be the relative reduction in HIV rate in some country. And covariates could be like some kind of characteristics of the countries. And then we record different countries and then see, I try to estimate this heterogeneous treatment effect. Here, for example, we might be interested in the conditional average potential outcome because we have the treatment is kind of continuous variable. So it's like some kind of range. And again, we would need to make the condition this like assumptions, for example, of the potential outcomes framework. But at the end, as I said, because there's this duality, so whenever we want to make those assumptions, we simultaneously think about causal graph. So we think, oh, how is it really that all the covariates, are they all kind of pre-treatment covariates? Because if we would include the post-treatment, that would give us a biased result. But at the same time, we also kind of think about those assumptions, or are there no other hidden confounders or not? Yeah, and now we move to the causal machine learning models. Like once we kind of are okay with the problem setup. So as I said, we make assumptions to basically know that it is in principle possible to get this causal knowledge from the observational data. And the result, like the question of can we get this from data or not, is called causal identification. So it means that given the observational distribution, like infinite data basically, and the target quantity, we know that, okay, under the potential outcomes framework, this could be for example, the average potential outcome could be identified either through backdoor adjustment, that's the name of this formula, or the inverse propensity of treatment weighting. I think you might have heard those terms. So it gives us identification formulas. But if we actually just have a finite amount of data, of course, we can just kind of estimate the parts needed for this formula calculation and then just plug them in. But there is way more there is a better way, more efficient way, efficiency in the statistical sense, saying like we can design such an estimator with like the lowest variance possible. And then here we use the achievements of the semi-parametric efficiency theory. It's also called Newman orthogonal learning, which would give us kind of an estimator which, I mean, intuitively speaking, kind of combines both formulas and achieves the lowest possible estimation error. Sorry. Yeah, and when you choose the causal machine learning method, you basically you ask the question, what would be the best machine learning model in the given the finite data. So we because we already established identification, and now we talk about different kind of estimators or different ways to learn our effects. There are a lot of also challenges. For example, now we move back to the heterogeneous treatment effect. For example, now it depends on the covariates. So now we talk about the conditional average potential outcome and conditional average treatment effect. And we see that to learn both, they kind of both suffer from selection bias. So you see there is some data where we have age and body mass index as covariates. And we have treatment like blue is not treated, orange is treated. And we see that in these regions there are more people who are not treated. Here there are more people who are treated. And essentially, like in this region, you don't know what would happen to people if they were actually also not treated. But that's, for example, that's what conditional average potential outcomes tries to predict. And for treatment effect, it's even worse, because again, for every single individual, you don't know this difference. So you cannot really build a regular machine learning model. And essentially the choice of the machine learning model to learn this heterogeneous treatment effects, we need to answer the two questions. It's like how to effectively address the selection bias. Should we do like some reweighting? Should we do custom losses? And how can we incorporate different inductive biases? For example, how can we have some regularization of models for predicting capo and Kate? And speaking about methods, for the potential outcomes or treatment effect prediction, there are generally two bins. So there are meta learners and model-based learners. And meta learners, it's not the meta learners which we have in terms of the few-shot learning. It's rather kind of this very specific term in the causal machine learning community. Here we mean that we have some kind of learning algorithm where we have like several stages, and at every stage we can put whatever model that we want. So it's we are free to choose the model there. And so, for example, we can use a decision tree or a neural network, etc. And model-based learners can try to either build the end-to-end model or build like model-specific algorithm. For example, we have like causal tree or causal forest. We have the full stream of literature on some kind of end-to-end representation learning methods to leverage neural networks. But overall, overall model-based learners could be thought as one-stage learners. So meta learners again could be split into one-stage learners when we just feed a single or regression with the treatment as an input, or two regressions for treated and untreated. For example, we have S and T learner. We can have two-stage learners. So, for example, we kind of derive some so-called pseudo outcomes, which kind of serve as surrogates, and which in expectation have the same value as Kate or capos. And then we regress the second stage model on that on the pseudo outcome. And this, if we do such a split, we can also say that model-based learners are often also like an examples of one-stage learners. Just a small recap on one and two-stage meta learners. An example for Kate. We have this two-stage of learning. So at the first stage, we feed the so-called nuisance functions. So it's kind of like a auxiliary regression or classification tasks, which then help to have this like final second stage to fit the final second stage model. So here we fit the conditional expectations of the outcomes and the propensity score based on the data, the regional data, and that we can take another subset of data and fit a final model, which would be the predictor of this tau x, the Kate, and the final model uses kind of a regional data set of covariates, and it kind of regresses covariates on those different pseudo outcomes. And the pseudo outcomes in expectation, they equal to the ground truth Kate. But we can also have a one-stage learner where we just say we fit nuisances, just the mu0 and mu1, and then we take their difference and we call it a plugin learner. There are, I mean, it's still a kind of ongoing research, like the kind of the description of all the pros and cons of every kind of learner. So, for example, we know that plugin learners are somewhat good if we want to have this easy interpretation as like one model. But if we actually know that the treatment effect is less heterogeneous than every potential outcome, for example, we might include some covariates which might be predictive of the outcome, but they do not contribute to the treatment effect. So with the plugin learners, it's kind of impossible to make a regularization for Kate kind of independently from regularization for potential outcomes. But then two-stage learners, they might be also tricky with they are sort of a little bit less interpretable. They might also suffer when we don't have enough overlap. So when we have patients who only got treated or patients who never got treated, and the inverse propensity weighted learner or GR learner, they would be very unstable. And in general, there is also a theory saying that like asymptotically, the GR learner and R learner are kind of the most kind of they are, if you like, they have the lowest error in terms of like the error from also estimating nuisance functions. But then in finite sample, there is no like silver bullet, so we cannot like have a nice model selection here. Just also a couple of words about this model-based learner. Oh, I think I completely missed questions in chat. Okay, that was good afternoon. Sorry. So a couple of words about model-based learners. For example, we might use like representation learning methods to, for example, if we have very high dimensional covariates and then we want to learn lower dimensional representations and then do treatment effect estimation there. It's a very, very interesting also direction, because here we say we might not have overlap, or like we might have, I mean, in this region, people got treated, not treated. In this, they got treated, but we have age and BMI. But then imagine our network could learn some representation which actually kind of coincides with the basal metabolic rate. And now we say in the space of basal metabolic rate, we suddenly have this overlap. And once we have overlap, it becomes easier to estimate the treatment effect. But there are also a lot of traps and how to say, tricky moments here, because we might also actually forget something useful, some covariate, and then we might induce confounding here. So this is also kind of a ongoing research stream. And in principle, like generally, just estimating treatment effects from with high dimensional covariates is a very challenging problem. Yeah. Just also want to say a couple of words. I think I have 6 more minutes. Just the current state of research in causal machine learning. It often, like, we already have a lot of methods. We have some methods which were proven to be asymptotically kind of optimal or having the lowest error, but in a finite sample, like not asymptotic regime with a finite data regime, there is still a lot of work to do, especially in the area of like model validity and different robustness checks, etc. And essentially, yeah, you might imagine causal machine learning is somewhat a more complicated version of the traditional machine learning, and many aspects of traditional machine learning are just either were proven to be not available or are very complicated. So as I said, model validity, for example, the task of model selection is very challenging. Also the question of like, okay, what if actually there are hidden confounders? How can we like quantify that? How can we measure that? Or we say, for example, we can build sensitivity models. When we say that we kind of allow for a little bit of confounding, and then what we get is not the point estimate of the Kate or the ATE, but the whole kind of upper and lower bound. This is called partial identification. We might also be interested in spillover effects, for example, when, like in the epidemiology, when I get a vaccination, it does not only affect me, it also kind of affects other people. So they get the chance of them being infected gets lower. So you might have kind of interactions between different people. Also in different extensions to more complicated settings, for example, with continuous or high dimensional treatments, it's an open research question. Or when you have a time dimension, also the question of missing data or censoring or and selection bias, the question of data fusion from multiple environments. When you say I have one RCT or one RCT and one observational data, how can we fuse it together when we have several observational data sets from different environments? Super interesting. Okay, some messages. And also the constrained machine learning in terms of can we build private treatment effect estimators, or can we have interpretable treatment effect estimators? Also, even the whole, I think the last aspect of uncertainty quantification is more like my PhD research topic. So how can we model both kind of uncertainty of estimation or uncertainty of the potential outcomes themselves, or together, for example, predictive uncertainty, and so on. Here are the slides with, for example, when we, the research direction with the model validity, we might want to weaken assumptions. So we might kind of have more realistic view of the world, but then we have less kind of informative treatment effect predictions because we get this upper and lower bound. We might have extensions to the time varying scenarios, also to the continuous or high dimensional treatments. And again, you might have the prediction of, for example, the point estimate of the potential outcomes might be one thing, but then the distribution of the outcomes would be like way different. And this is also important for making decisions which are reliable, or like making this kind of personalized policies. And yeah, again, thank you for attention. I'm happy to hear your questions. And yeah, again, here is our kind of vision for what machine learning could bring for treatment effects prediction, and then also design of the personalized treatment policies.
Okay, well, thanks a lot, Valentyn. Well, any questions from the audience? I don't know if anyone has any kind of question regarding this webinar.
Maybe it was very simple or very complicated.
Well, I don't know. Let's see. Well, in any case, in the meantime, I can ask you maybe a couple of questions.
Yeah.
So, how do you think these causal ML advances could be integrated into practical decision-making tools in medicine or in business? And I mean, what do you see as the main obstacles for their broader adoption?
Yeah, it's a very interesting question. I would say the model validation is the trickiest part, because I mean, there's one situation where we say we assume there are no hidden confounders, but then in reality there could be. And the other thing would be that in order even to choose, like, okay, we can have several different models that predicate, but then it's very hard to kind of reliably choose one. There are only like proxies for the model choice. And ultimately, if you would want to deploy the personalized treatment effect predictor, you would have to check it with randomized controlled trial data. So, of course, at the end, you are stuck, and you would, in real world, it would be required for this model to be kind of evaluated with the RCT. For example, we even like to deploy it to treat real people, you would have to, for example, compare it between like the current treatment policy versus this personalized algorithm, and the kind of the policy value of that should be like your personalized treatment effect predictor should achieve better policy value. So essentially, yeah, I mean, you would still have a need for RCT data. So I would say that's the main.
Okay.
Because I mean, I know there are a lot of research also in this recommender systems, for example, at like this big IT companies, but because they have the access to A/B tests, so they can, whatever model that they fit, they immediately could like deploy it for like half a day or the 1 week and then see the result. So for them, it's like super easy to make this RCTs with the model. With the medicine, it's way more expensive and way longer.
Okay, perfect. Thanks a lot for your answer. So Natalia has a question, but she has no mic there. So the question is, when there's no ground truth, is the common practice in today's research using toy academic datasets? Is this enough? That's the question.
Toy academic data. I mean, did you mean synthetic data sets? Or yes, I think, yeah, it's also a very nice question. If you would read the causal machine learning papers, you would see, they all use the synthetic data sets, but that's rather the concept. It's like a concept of a proof. Well, proof of a concept, and you don't really of course, it's nice that it works on the synthetic data set, but then if you have a kind of brand new data set from real world, you don't know how similar it is to your synthetic data sets. So you would see. So I would say the synthetic data sets, they just you just show that your method works in principle, but as again, there is like no free lunch. The no free lunch theorem says there is no universally best method, and then you would still need to do some sort of tuning for the data set at hand. So yeah.
Okay.
I hope I answered the question.
Yeah, Natalia says yes, thanks. So
yeah. I think also the problem of having no ground truth is actually very. I mean, we are getting dangerously close to kind of pseudoscience, because I mean, at the end, you would have to prove everything with a randomized control trial, and also, like in randomized control trial, you don't really have the ground truth individual treatment effect or Kate, but you have some sort of proxy to that. So you say in a little, like some subgroups, you can still do you can check the can like divide by age and then like stratify by age, and then see in every age subgroup you have both treated and untreated. But of course, this like super personalized treatment effects, they get harder and harder to like validate. Yeah.
Okay.
Yeah, but very interesting question. And yeah, I think I only heard there are like a couple of actually like the couple of medical papers from I think Australia, where they have this full pipeline of having observational data, then having small RCT subset where they kind of did the model selection, and then they conducted another RCT where they basically showed that this personalization actually is way better than the current treatment practice. Yeah.
Okay, so thanks a lot for your answer. Any other question from the audience? More questions? No? Well, I have a very last question for you, Valentyn, if it's okay.
Yeah.
If I'm not mistaken, you have worked as well with causal transformers for estimating counterfactual outcomes. I don't know if you could tell us a bit more about this research line and what kind of, let's say, modifications you do on the usual transformer to perform these kind of tasks.
Oh, yeah, interesting question. I think it was my sort of first paper during my PhD. So there are like, let's say, if I would do it right now, I would do it a little bit different. But essentially, the causal transformer is more like a plugin learner, but with additional kind of representation learning tricks. So I also applied the balancing. And then it is also like a time varying model. So you have for every patient, you have some kind of previous history of them being treated and their outcomes and their covariates. And then you say, what would happen if I apply the sequence of the fixed treatments in the future? So it's kind of like basically Kapos prediction. Yeah, Kapos prediction, but in time, and where it's not just 0 or 1, but it's the whole kind of trajectory of zeros and ones. In a short, to put it shortly.
Yeah, I understand. Okay.
But overall, if I would, I think I lately I got super fond of this kind of doubly robust, so-called doubly robust, or like GR learner or R learners. I think the general name is numeral orthogonal learners, and for them you they were proven to be asymptotically optimal. But the causal transformer is just kind of this like a plugin learner. So if I would do it now, I would do it a little bit more advanced.
Well, that happens to all of us with our research, right?
Yeah.
So after some years, we think that we should have done it in other way.
Yeah, but if you've seen one of my colleagues, Konstantin, he did this G transformer, which is way more theoretically grounded paper, which builds upon the G on the causal transformer, and that's more like a regression adjusted learner. So yeah, if you are interested, I would really recommend reading that paper, and that one is more theoretically grounded.
Okay, so thanks a lot for your answers. And now, well, any other question from the audience? Your last chance. Any other question? No? Okay, so we can thank our speaker again and see you on the next DaSCI seminar. Thanks a lot, Valentyn, for accepting our invitation. It was a pleasure to have you.
Yeah, thank you for the spotlight. Yeah, thank you.
It's perfectly fine for us. It was really interesting. Thanks and congratulations for your research.
Thank you. Thank you.
Thank you. Bye-bye.
All right, have a nice evening.
You too.